Hi, my name is Jenna Williams, and this is a tutorial for creating a PERFORM-3D concrete shear wall after the Thomsen Wallace wall from their 2004 paper. This tutorial was created for Cal Poly SLO's ARCE 511 course, but it's intended to be a PERFORM-3D concrete shear wall tutorial for anyone who's interested in how to properly model these walls. To give you an outline of what we'll be going through, first we'll start with a background on RW2, the Thomsen Wallace wall. Then we will look into some PERFORM-3D basics for setting up your file and getting familiar with the controls. Then we will model the wall and, of course, analyze the wall. And finally, we will compare the experimental test results to the PERFORM-3D hysteresis that we obtained from this test. To give you a background on the Thomsen Wallace RW2 wall, it's a 12-foot tall, 4-foot wide wall, F'C of 4 KSI, Fy of 60 KSI for the rebar. If we look at a cross-section of the wall, we can see that there are number 2 rebar spaced at 6 inches, and the wall is confined by number 3s at 3 inches on the ends. The Thomsen and Wallace, when they ran this experimental test, they created this hysteresis, and this will be what we're aiming to get out of our PERFORM-3D model. So just sort of this is our goal. This is what we'd like to see. For those of you in ARCE 511, we previously created 2 different bilinearizations, a Priestley and a Cumbia bilinearization, to find a force displacement response of this wall. And we found that they overpredicted the displacement compared to the experimental test. And this experimental test was displacement controlled, but it still showed us that maybe we need to do something more than just a simple bilinearization to describe a cyclic load test. And so with our PERFORM-3D model, we'd like to see what results we'll obtain and how they compare, because now that we're not just looking at a static pushover, we're looking at the entire hysteresis, as you saw on the last slide. We'd like to see if our PERFORM-3D model can capture cyclic degradation, energy dissipation, all that other great stuff. So now we will dive into some PERFORM-3D basics. Our PERFORM-3D basics start with opening PERFORM-3D. Once you have opened PERFORM-3D and it's found you're licensed, it will ask you if you'd like to start a new structure or open an existing structure. We'd like to start a new structure. We're going to start with things that we can't change later, so remember that once these are in, this is what PERFORM-3D will be using, and then we'll look at some things that can be changed later. But first, let's name our structure. I'm just going to name it RW2. I'm going to want my forces to be in kips, and I want to keep my length in inches. I'll leave my gravity as 3D 6.4, and I'd like the location of my structures folder to be user defined. When it defaults, PERFORM-3D will put your structure within PERFORM-3D's kind of like program file stuff, and I'd rather say I want it a certain place, and so I'm going to go to my documents, and I already have a folder called 511, and I have a folder ready, but you can also create a file if you'd like to at this time. Since I've specified where I'd like PERFORM-3D to store my model, I'm going to name what the structure is about. PERFORM-3D does this a lot, where it lets you add descriptions to whether it's output data or input data, just so that maybe you can remember what this model is for. And so I'm going to start with, I'm probably just going to leave it actually the same as the the structure name. We can also pick the minimum spacing between nodes. For most things that we're working with, the closest we'd ever want two nodes to be is 6 inches, so we'll just leave it at that. If you're working on a larger scale, maybe you'd set it at 60, but for what we're doing and the scale of the wall we have, 6 inches is just fine. You also can ask Perform-3D to save the model at intervals. Depending on how complex you're working, maybe this would be 5 minutes. I'm just going to set mine at 10 minutes. But again, this is in that part of your Perform-3D setup that you can change it later. So depending on what you're working on, you can modify this. Also, it asks you if you want to have Perform-3D beep whenever there's an error message. I just leave that on so I know if Perform-3D is mad at me, I can fix it pretty quickly. So once I have these settings picked, I'll just click OK. And now I can choose a task. So up in the left corner, we can see the main buttons that come up first. You have File, where you can begin, open, save, save as, delete, pretty standard stuff. Phase, where you can choose the build or analysis phase. Personally, I just use this, which is for the modeling phase, and this, which is for the analysis phase. So depending on, oopsie, yeah, sometimes it gets a little mad. So depending on what you're working with, I would just use these buttons across the top. You do have also task, which will just tell you what options you have within build or the analyze states, but I just tend to use these buttons right here. If you'd like to save the structure at any point, you can click save right here. If you'd like to save your structure as a new structure, say maybe you've gotten to a point where you like your old model, but you'd also like to explore something new with your model, you can save your current structure and create a new name for it with whatever modifications you might have. And you can see again, it asks you to create a description. Perform-3D only lets you create titles that are 12 characters max, so that's sometimes limiting, so make sure to name things smartly. Let's start with the modeling phase of our tutorial. First, we will be heading over to the Nodes tab. So up here on the left side of the screen, you can see me pointing to 4 dots. We're going to click on that. And the first parts of our model involve adding our nodes, and with that, the supports and the slaving and the modal mass that go along with it. So as you can see on the right side of the screen, we're going to be adding nodes at each of the intersections of these red lines. The red lines represent how we'll be breaking up the wall into our mesh. We've decided to horizontally mesh it according to the type of material that exists in each part of the wall. On the ends of the wall, we'll have confined concrete in 6.75-inch wide meshes, and the 2 center sections of the mesh are 17.25 inches wide, and we'll have our unconfined concrete. And we've decided to break up the vertical mesh into 12-inch tall pieces, which should be adequate for the analysis we'll be performing. We'll also be adding fixed boundary conditions, these yellow dots at the bottom of the structure, and we'll be adding a horizontal rigid slave on the top nodes of the wall to enforce that they stay in line with each other when we're going through that cyclic load test. So let's go back to the left side of the screen. We'll start by adding a single node into our blank paper space. So let's go ahead and specify 0, 0, 0. Let's test this node. And the black space will be recentering each time you add a new node. So the first node you add is going to end up showing up in the middle of your screen. We're going to click OK. We would like a node there. And our following nodes I've laid out in this table right here. So if we'd like to put a coordinate next to the 0, 0, 0. The next node over will be at 0, 0, 6.75, and those coordinates are written in this order, V, H2, H1. So if we want our V to be 0, our H2 to be 0, and our H1, we'd like it now to be 6.75. We will click test. Okay, you can see that it's put the two nodes in a straight line. Right now we're seeing a 3D view. If you don't care for the 3D view, we can also look at a plan view or an H1 view, which is I guess it's a elevation in the direction of the wall. We won't be building side to side in this plane. So probably the best view we'd want to look at is H2, which is a nice elevation. So our next point next to 0, 0, 6.75 will be 0, 0, 24. So 24, 0, 0, test, great. Our next point, 0, 0, 41.25, test. Oh, what did we do, Ron? Oh no, we put in the wrong node. We wanted to put 41.2500. We can click undo, and that node won't be there anymore. Awesome. So we'll just fix this. 41.25, test. Okay. And our last one on the bottom row will be 48, sorry, 0, 0, test. Okay, awesome. So we have our first row of nodes. It would kind of be tiresome to go through adding all of these nodes. So instead, we're going to use duplicate. And we're going to select all the nodes we'd like to duplicate. And we would like to move them up, which our up direction is the V direction. And we'd like to move them up 12 inches, as you remember me saying. So we'll just put a 12 here. The other two spaces can remain blank, and they'll just be taken as 0. We will say test. Voila, we now have our new row of nodes. Our next ones will be at 24. Test. Great. And we'll continue our way up following the table that you'll see on the right-hand side of your screen. As you can see, the screen is still readjusting its size each time we add a new row. PERFORM-3D does not like to waste space or give you extra space, so it'll always tend to show you exactly what's in its screen. If you'd like a wider view, you can play around with these buttons down here that let you change the orientation. But for this simple wall, we don't really need anything more than the basic and the H2 views that they give us. Okay, so this is now all of our nodes, everything that we'll need to create our wall. As we remember, we still need to add our boundary conditions and our horizontal rigid slave, so let's go ahead and do that. We're going to go to supports. It's the next tab under nodes. We would like the bottom of the wall to be fixed, so we're going to select those nodes, and we are going to choose the fixed option for our support types. We're going to say test, and you will see that it looks fixed in this view, but perhaps a better view to view this in will be the basic, so let's just click OK. If we go to the basic view, we can see that all of them have this kind of crosshair on them, which means that they'll be fixed in both directions and in rotation. Next, let's move along to masses. We're going to add a modal mass at the top of our wall in the case that maybe we want to later use that for something else. It won't be necessary for our cyclic load, but it'll be good to have. We will just make it a unit of 1 and we'll add it to the top nodes of our wall. Test. Okay, it's added the modal mass in both the H1 and into the page, the H2 directions. Again, not necessary for what we're doing today, but it will be nice to have in case we do want to end up running some other tests. Now let's move on to slaving. I mentioned we wanted to keep all of these top nodes on our wall moving together, and we will do that by adding a slave. We will need to select that we'd like a new constraint set, and we would like that constraint set to be a horizontal rigid floor. So we're going to click New, and I'm just going to call it that. Horizontal, oops, can't spell, can I? Horizontal rigid floor. Okay. And as you can see, it doesn't really like super long names, so it's actually horizontal rigid flow. And we're gonna go with the flow and accept that. Let's select all the nodes that we'd like to be part of that rigid floor. We're going to click OK. And now they will hopefully be moving together. All right, so that is everything for our nodes section. All right, moving on from our node section, let's go ahead and move forward to component properties. Go ahead and click on the button that is next to the nodes button. It looks like a little graph. All right, and before we dive in, we're just going to take a quick little look at what we'll be doing in this section. A great reference for you to look at is a paper by Lowe's et al. From 2018. They did a great job at summarizing what the PERFORM-3D inputs really mean and how they will affect your model. And so there's a couple different parameters that we'll be using to help define yield strength, ultimate strength, and the strains that correspond with those actions. And I've put them out in a table right here. We're going to be using a couple that are from the Lowe's et al. Recommendations in that 2018 paper, but we'll also be using some for rebar that are specific to this project and just from recommendations that I've received from industry on how to model rebar. So let's start with our concrete. So we're going to click on materials. We will go to inelastic 1D concrete material. We will click new. And we will specify it as, let's start with the unconfined. So unconfined concrete. We're going to click OK. Now let's start by inputting what those properties are. Our modulus of elasticity is 3605. Oh, and also some other things that we'll need to do. Let's make sure that we want the shape of our relationship to be trilinear. We don't need to include tension strength for this model. We don't need to include strain capacities. Our cyclic degradation, we would like it to be YULRX, and the only way we're going to get that option is by clicking yes for strength class. And then we can add YULRX. And for this project, we don't really care about upper and lower bounds. All right, so now that we've done this, I was jumping ahead. Let's go ahead and add in all of our properties. Our modulus is 3605. Our Fy will be 2.5. Fu will be 3.33. Du will be 0.002. and dx will be 0.011. Again, the way we're calculating and choosing these values is based off of this table to the right. Next, let's go ahead and move on to our strength loss portion. For the strength loss portion, we will be choosing for DL 0.00202, DR will be 0.01, and FR over FU will be 0.001. All right, what's next? Cyclic degradation. We'll be adding those factors that are over on this table to the right. So we have 1, 0.4, 0.4, 0.1, 0.1. Great. Let's go ahead and check this relationship. We can see that PERFORM-3D has provided us with a graph that we can look at what's happening. If I go back to this previous slide, you can see what all of these points really mean. So right here, we're experiencing the initial stiffness of the concrete. Next will be that hardening stiffness it goes through. And then we have strength loss that occurs. Pretty straightforward in that respect. Again, this is on the compression side, and then we see that we don't have any tension strength. All right, now that it looks like we have our unconfined concrete material complete, let's go ahead and click Save. Make sure to always click Save between materials and often, because if you don't and you go to click a new box, Perform will forget that information. So it's really important to make sure that you're clicking that Save button. All right, our drop-down menu only has unconfined concrete, and we'd like to add confined concrete to that. So let's go ahead and click New. We'll call it just that, confined concrete. Okay. And what's next? Let's make sure that we chose trilinear, strength loss, YULRX, no strain capacity, and no tension strength. And we'll go ahead and put in our values once again. 3605, FY will be 3, FU will be 4, DU will be 0.004, DX, which if you look over at, where am I going? It's not on here, but DX is calculated in relation to where these other values are. We're going to use 0.031. On the strength loss side, our DL will be 0.00404, DR be 0.029, and our FR over FU will be 0.2. Let's go ahead and check this setting. Oh, looks like we forgot our cyclic degradation. PERFORM-3D was nice enough to remind us. We'll go ahead and put in those values like we did for the last one. 0.1, 0.1. All right, do you think it'll be happy now? Let's check. Awesome, this looks like the curve that we want. So we're gonna go ahead and click Save. Great, now we have both of our concrete materials. Now that we have both of our concretes, let's go ahead and add our inelastic steel material, non-buckling. I'm going to click New. We will add, we'll just call it rebar since we only have one type. We would like a trilinear relationship. We would like symmetry. We would like strength loss. Again, this is not a Lowe's recommendation that we're using for rebar. This is sort of from experience of modeling these walls. I'd suggest that we use a strength loss model. We will be using YULRX for our cyclic degradation, and we don't need strain capacities for this model. Let's start with our E is 29,000 KSI. Our FY is 60. Our FU is 75. Our DU will be 0.045. Our DX will be 0.1. Strength loss, we will be putting 0.05 for DL, 0.07 for DR, and our FR over FU will be 0.2. And we would like the strength loss interaction to be set to 1. Cool. Let's go ahead and check these properties. Oh, we forgot our cyclic degradation. Again, Perform-3D was nice enough to remind us. Let's go ahead and input 1, 0.4, 0.4, 0.1, 0.1. Great. Thanks, Perform-3D. All right, let's look at this relationship. This looks great. So you can see we have strength loss here at about 0.05 strain. A model without that would have just kept hardening and wouldn't have had any strength loss, but we would like to include that for this model. Let's go ahead and click Save. We've added our inelastic materials, but we also still need to add this last item on the PowerPoint, elastic shear material. So let's go ahead and click under here. We have elastic shear material for a wall. We're going to click New. We will call it just that, elastic shear material. We'll click OK. And all that we need for our elastic section will be a shear modulus. And per the Lowe's recommendations, they suggest to use 40% of the modulus of elasticity for concrete. And if you remember, our modulus of elasticity was 3605. So I believe that our shear modulus is going to be 1442. We will click check and we will click save. Great. We have all of our materials. Now it is time to move past our materials and create cross sections. So on our Perform-3D model, let's click cross sections. And if we look back to the PowerPoint side of the screen, you can see the original drawing that I gave you of our wall. And we would like to transform that into something that we can model in Perform-3D. We've decided to keep the confined sections on the end and unconfined sections in the middle. So all of the confined concrete on each side is lumped into 2 pieces of rebar. And same thing in the middle, the unconfined sections. There's four bars in each of these sections, and they've been lumped into just 2 bars because we can't model the 2 layers of rebar. You can also see that we've chosen to make the unconfined section only 2.5 inches, or sorry, the confined section 2.5 inches wide instead of 4 inches, because the true area that will be confined concrete is only as wide as where those tie space, the confining ties are being placed. We can't say that that outer cover of concrete is going to be part of that confined concrete. But the unconfined concrete, we can consider it to be the entire depth. I've created a chart again so that we can easily add in all of our pieces for each cross section. So on our Perform-3D model, let's scroll down to wall sections, and we're going to choose an elastic section. We will click New Cross Section. Our new cross section will be confined cross section. We would like a fixed size. Auto size is great if you have a repetitive wall in a building and just would like the same rebar at the same spacing everywhere. But since we're just modeling one wall, we can be a little bit more particular of how we want to set it up. So we're going to click fixed size. Okay. Great. Now let's add the pieces that we'd like to be part of this cross-section. We're going to click Inelastic 1D Concrete Material. And since this is the confined section, let's add confined concrete. You can see from our PowerPoint, our first coordinate of that will be 1.6875. And our area will be 8.4375. And we'd like to draw it 2.5 inches thick. Let's add it. We'd also like to add the same property, but at negative 1.6875 as the coordinate. Add. Just so you understand that these aren't just numbers we're putting in, we can go ahead and go up to Draw Section. You can see that it's drawn the two pieces of concrete that we're interested in for this section. And if we like, we can highlight them and it'll tell us what's happening there. Cool. Let's go back to structural fibers so we can add our rebar. Inelastic steel material, non-buckling, rebar. We'd like to set the same coordinates, but now we'd like our area to be 0.44 to represent those end bars. And we would like the thickness to just be 0 because we'd like to perform 3D to recognize that this is a circle and not a square. Let's go ahead and add this section. We'd also like to add one that was at the negative 1.6875 coordinate. We'd also like to add one at the positive. Great, let's check our section. Awesome, this is what we want. So you can see all of our different fibers will light up when we click on them. And then we're pretty happy with what it looks like. The last thing we need to add to this would be our out of plane information so that PERFORM-3D knows what to use. Let's go ahead and add our Young's modulus of 3605 and our Poisson's ratio of 0.3. For our bending and torsion thickness, we'd only like to include what is not part of that outside concrete, so we're just going to use 3 inches instead of 4. Cool. Let's check this. I'm going to click Save. Great. So this section has been saved. We would like to, however, make a second section that is called Unconfined Concrete. We're going to click OK. And we will add things similarly to what we did last time, except now this is slightly bigger pieces. So our first coordinate will be 4.315. Our area will be 34.5. Again, this is in inches squared in case you're like, where are these units coming from? We're gonna again add the negative. Let's add our rebar. For this section, our rebar is slightly smaller. Cool, this should be all our pieces. Great, you can see the rebar looks a lot smaller because there is less rebar and there's more concrete in these sections. Our out of plane, we're going to again use 3605, 0.3. All right, let's click check. Awesome, save. Great. After creating our cross sections, let's create our compound components. So go ahead and click compound. I'm going to click shear wall compound component. We're going to create a new one. Once again, we'll have to create confined and unconfined compound components. So let's create our first confined compound component. Okay. For our vertical and axial bending, we'd like to use our confined cross section. We'd like our wall thickness to be 4. And our Young's modulus keeps asking us, and we have to keep giving it to it, 3605. our shear material. You'll remember we made this elastic shear material, and we'll use the same wall thickness there. And this is great. Save that. Let's add our unconfined compound component. Okay. We would like our shear wall inelastic section, but now we'd like our unconfined concrete. We'll leave the wall thickness, and we'll leave our shear properties with the elastic shear material. Check, save. All right, now we have all of our components. We created our materials, our cross sections, got all the way up to our big compound components that we can add to our structure. All right, we've created our compound components. Now let's move on to adding elements to our structure. So we will leave the component world and go into the element world. This will require us, if you look at the right of the screen, to add the elements, assign them properties, and then assign them orientations. Let's start with adding our elements. We're going to go to Add Elements, and we'd like to, ignore that. We're going to start a new element group. We're going to call it Shear Wall. We're going to name it Confined Group. We'd like geometric nonlinearity, P delta. We'd like to say yes. And let's add our confined concrete group, since that'll be on the ends. We'll add that in columns. And we will click on the nodes 1, 2, 3, 4. So 1, 2, 3, 4. Test. All right, great. Let's add the next ones. 1, 2, 3, 4. Test. Awesome. Now we'd like to add another group for our unconfined concrete. We'll just change the title to unconfined. Okay. We're going to, once again, but now we have 2 rows, right? So we might as well just use grid. 1, 2, 3, 4. Test. Okay, great. And what you'll see now is that depending on which group I'm looking at, it's called my current group, and I can toggle between looking at them. However, these groups, we've just typed in the names of them, we haven't given them properties. So we will need to assign them properties. Make sure that your current group is the confined group. Go ahead and highlight all of those walls. Click Assign Component. We're going to choose Shear Wall Compound Component, and look at that. We can choose our confined, our unconfined. Make sure you choose confined. Going to assign. Great. Those are now all assigned. If I click clear and then I click on one, you can see that it's been given the confined compound component. Great. Let's do the same for our unconfined group. We'll go ahead and select all of those walls, or all of those elements. My apologies. Assign, shear wall compound component, unconfined compound component, assign, and we're great. Everything's dandy. And let's see, what did we forget? We need to assign orientations. As you can see from the PowerPoint, the orientation we would like is that since our elements are already positioned with IJ, KL, that sort of square configuration, we'd like the axes, the 2 to be parallel to the IK edge and 3 to the IJ. So we're going to go ahead and click here. We'll make sure that we've selected all of our elements, test. Oh, we need to choose an axis orientation. axis 2, test. Okay, and if we go to basic, we can see how we've set them up. And we've made it so that H1 is positive this way, H2 that way, and V up and down. Let's go ahead and select our other group and make sure those are all oriented the way we want. IK, test. Great. Now all of our orientations and properties and groups are set. Let's move on to load patterns. So that'll be 2 buttons over from your elements. We don't have any yet. As you can see from the PowerPoint, we started with a 96 kip axial load, and we're just characterizing it as a 1 kip lateral load that will be cycling back and forth. So let's go ahead and start with the gravity 96 kip load. So we'll say new load, gravity load. Okay, since we're just applying it to the top nodes, I've decided to break it up according to tributary area. So our outside nodes will be getting 6.75 kips, and you'll see when we add these why I've drawn them over here up with a negative sign, because that's how they draw them in the model. So we'd like this V force to be negative 6.75. We'd like to replace anything, but add is the same for this. And we can see that we have that force there now. The middle nodes, it looks like we're going to choose negative 24 kips. Select. Great. And then we'll be adding that middle one, S34.5. Test. Okay. Great. Our gravity loads are in. Let's go ahead and move to lateral load. And we just have it distributed across the top. Once again, since we have that rigid, the rigid slave, it should be distributing it, but we're still going to break it up, each node. We'd like all of them to be 0.2 kips. I'm going to test. Great, that looks like what I would want it to be. Awesome. Now that we have our nodal loads in, it is time to move on to drifts and our structure section. Our drifts button is 2 buttons over from load patterns. We're going to add a new drift, and we'll call this roof drift. And it is a simple drift, and it is going to be in the H1 direction. We need to choose an upper node and a lower node. Our upper node will be here, and then our lower node will be right down at the bottom. Test. Okay, so it'll be measuring drift in the positive H2 direction. This is great to know for our analyses that when we're creating our cyclic load steps, the first step will be positive in this direction, and then we'll be going negative in the other direction. So it's important to know those basics. Let's create a structure section. A structure section will allow us to create our time history analysis for the cyclic load. PERFORM-3D won't automatically create the hysteresis for us, so it's important that we take a section cut at the bottom of our structure. Let's create a new section. We're just going to call it base section. We will specify coordinates. Our H1 will be the middle of the structure, H2 will be 0, and our height will be 0. That'll be where it cuts the structure. We would like this to be along IJ, base, and we're going to choose, as you can see right now, we're only in one group. I'm going to click OK. Those 2 have been added to the base section. Let's make sure to choose from our unconfined group 2. We'll choose these 2. Okay. Awesome. So you can see that depending on which element group I'm in, it'll show the cut. It'll show the elements it's cutting through, and it'll show wear on that element. And you can see that with the green dots. Those green dots represent where that base section cut is. All right, we've set up our model. That is the end of the modeling phase. Time to move on to analysis. We have one final step to take in our modeling phase, and that will be adding our limit states. So right up in the left corner next to the structure sections is a little thumbs up. So let's go to limit states. We're going to add a drift limit state, and it looks like we'll need to create a new drift limit state, and we're going to call this roof drift. And it will be related to that roof drift that we set up a couple minutes ago. And we're going to leave it as this roof drift, and the limit at this point won't matter too much because we'll be using max allowable controlled drifts to set up what it goes to. So we can just leave these as positive and negative 0.1, which would be 10% drift. But again, we're not going to be going out to that. This is just to allow it to go within bounds that are underneath that. So we're going to click save. All right, now we have completed our modeling phase, and it is time to move to the analysis phase. To start the analysis phase, we'll start by clicking on the analysis phase button. It's right next to the crane where the modeling phase is. So let's go ahead and click analysis phase. It'll ask us to choose a task, and the first task we'll be doing is setting up the load cases. And the way we'll be setting up our load cases is we'll have our gravity load, and then we'll have a set of different cyclic load cases. So let's start with our gravity load. We'll click new, and we'll just simply call this gravity load. Okay. This analysis for gravity is going to be linear. We'll just apply all the gravity load in one step, and it'll be a nodal load. Our scale factor is 1.0. We'll click add, and that is our gravity load. Let's click save. All right, we've created our gravity load case. Let's now add our cyclic static pushover cases. If we look over to the right side of the screen where the PowerPoint is, you can see that I've created a chart for each of our cyclic load cases. We'll be cycling back and forth from cycles of 0.1% out to 2.5%, which is about where the experimental testing analyses were taken. You can see those load cases are in the first column. The second column indicates the drift that those load cases will be creating. So the first case is 0.1%, which means that the allowable drift is going to be 0.001, which is 0.1%. In order to get to the next load case where we're pushing the ball the opposite direction to negative 0.1%, we'll need to cycle from that positive 0.1 all the way to negative 0.1%, which means we'll be going through 0.2%. And that'll be in the D along H1, that's negative direction. And so we'll cycle back and forth, and those drifts add on to each other. Since, again, we're going from one positive position to a negative position, it's not simply that 0.5% positive will mean our maximum allowable drift is 0.5. We have to add on that negative 0.1 that it originally came from. Let's start with our first pushover case. We're going to click Create New, and our load case name will be positive 0.1%. Okay. Our number of load steps will be 50, and our max events in any step will be 100. These are just from the PERFORM-3D user manual. Initial step to first event, we'd like to say yes. Our maximum allowable drift will be 0.001. We will be using a displacement pattern. So our first point will be 0, 0, 0. Our second point will be at the top of the wall. The D along H1 will be positive 1, and our D along H2 will be 0. Our limit state to stop the analysis will be a drift. We'd like to use that roof drift limit state that we set up, and that'll be our first step, and we'll click Save. In order to utilize these settings again, since the only things that will be changing each time are this maximum allowable drift and this d ln h1, we can now, after we've saved it once, we can click Save As. We'll just rename this the next load case name, and we'll change what needs to be changed. So this will now be 0.002, and this will be -1. We'll click Save. Again, we'll click Save As, and we'll call this the new load case name. Now this is 0.6. So will be 1. Save. Save As. Negative. Okay. If you get the idea and you feel confident about these, feel free to either skip ahead or pause the video. I'll just walk through each of these. All right, this looks good for the negative case. Now I'm at positive 0.75%. Okay. 125. Positive 1. Save. Save as. Negative 1.5, and now this is -1. Save as. Positive 1%. Now we're at 0.175. 1. Now we're at positive 1.0%, or sorry, we're now at 1.5%. .03, and we'll be at -1. Almost there, we're at plus 2%. Nope, 0.035. Feel free to take this part slow to make sure that you're inputting everything correctly. All right, and our last case is 0%. This case will bring our wall back to its neutral position. And we only need to go 2.5% because it's only traveling to the middle. It's not traveling past the neutral position again. We'll click Save, and that is all of our load case setups. Now it is time to move on. Our next step will be to set up our analyses. We are going to start a new series, and we will just call this cyclic. If I can spell cyclic, yep. And this description, I'm going to put gravity load plus cyclic load cases. Again, just another description that PERFORM-3D allows you to help identify what you're running. Our type of load sequence is going to be general. For now, we're going to say we don't want to include P delta FX. Our number of mode shapes will be 3. The number printed is 0. I think I mentioned this earlier, but for this analysis, we're not trying to look at mode shapes. The modal mass scale factor, though, we'll leave as 1. As you notice, we're just filling things out in this basic and masses. We're not dealing with modal damping, Rayleigh damping, upper-lower bounds, or anything else. We're really just interested in this basic setup, but the other things I would encourage you to look into at a later time. Let's go ahead and click. First, let's check our structure to make sure it's stable. No errors were found. Okay. And now we can click OK. All right. We've set it up, but now it's time to figure out what needs to be run. First, it will, of course, put in these mode shapes, but after that, we'd like it to run the gravity load. Now we'd like it to run through our static pushover cases, and we'll start at the +1. And we'd like it to add on to the first analysis number. So since this is 1, our next step will be adding it to the last one. So we'll go ahead and add that, and then we'll add our next case. Really triple and double check that you're adding all of these in. It's really easy to lose your place and forget one, but it's something that you'll recognize pretty quickly once we've run the analyses, is that the time history might look a little funky because you're missing a step. In total, it looks like you should end up with 16 different steps. I'll go ahead and scroll to the top and click through it slowly for you. So there's the first 8. And there's the rest of the steps. And this is it. We've created and set up our analyses. Now it is time to run the test. So we'll go ahead and click Run this set of analysis. Go. And now it is running the case. It shouldn't take too long. Again, this is just a single wall. It's not an entire building, so it's not costing PERFORM-3D a lot computationally. And if you're watching the screen that's being shown to you right now, you can see it stepping through each of the load cases. So right now we're at -1%, and it takes 50 steps to go through that cycle. Now we're at +1.5%, etc. Feel like I need Jeopardy music, but looks like we're done. All right, let's click OK. And now it shows that we have run down here. It'll show us previous analyses in this series. This is what we have run, and it looks great. It looks like all the loads were applied. It didn't freak out. Over here in the status, if it had failed at any point, it would have shown us that on this side, but it looks like our structure isn't ill-conditioned or anything. So now it's time to see that hysteresis that we've been working so hard to get. So let's go ahead and go over to time histories. And If you remember earlier, we created a structure section, so we're going to go to structure section. We'd like the H1 force, and we'd like multiple loads that went through that, and we'd like all of our cases to show so that it'll show the time history or the hystereses that we're looking for. Click select all. You can see that those green dots have shown up again at our base section, since that's what we've chosen, the section we've chosen to look at. We'll click plot. And it looks funny because we're not at full screen, but let's go ahead and go to full screen. Now that we're at full screen, it's a little easier to see the shape of our hysteresis, and we should be pretty happy with how it looks. You can see that out here, it gets to, it looks like around 0.02642, which is 2.642% drift. You can see that our axes look a little funny in PERFORM-3D, so just be mindful of what units we're looking at. So here it tells us our forces are in kips. If maybe you don't want to look at shear, at the base shear, but maybe you'd like to look at the moment, we can look at moment about H2. Same thing, make sure we're in multiple loads, we select all, and you'll see again a hysteresis, but instead of plotting reference drift versus base shear, we're now plotting versus the base moment. For post-processing this data, because I don't particularly like just looking at these graphs, I'd like to make my own graphs that are a little bit more legible. I'd like to save the data, so I'm going to go back to the H1 force plot. And to save the points that it's created and save this graph, we're going to click up here, and we're going to say, save these results to a file. Once again, PERFORM-3D offers just saving it to a default folder, but I'd like to define where this is saved. I will go to Documents, and the folder where I'm keeping all this stuff is right here. Great. Just leave right here. I'll say OK. I'd like to just name the file T and W cyclic, and I'll just put that right here. Cyclic load hystereses points. And it'll be saved as a text file. So save, OK. And just so you know what those results look. And now you can see that this folder, it's been saved to my live tutorial folder as a text file. And that text file looks something like this, and it's just all of the data points with a little bit of text at the beginning to tell us a little bit about it. So I'm going to post-process this, and we'll go back to the PowerPoint so you can see how this compares to the experimental results. All right, so now that I've post-processed the data, let's take a look at the results comparison. From this very rough graphic, you can see how the PERFORM-3D in orange compares to the experimental testing in blue. It looks like our model had a slightly higher initial stiffness, and that might have led to it not creating quite the same loops at the end that we see in our experimental test. But overall, it looks like we have a fairly successful model. Good luck in your future wall making, and thank you for watching this tutorial.